Just a quick disclaimer before starting the video. I am not a mathematician. These are just my notes and impressions based off of self-study. If I at any point am imprecise with a proof or mess up an example, please leave a comment. This helps me learn, helps me develop, and I would greatly appreciate it. If you get something out of the video, please consider liking, subscribing, and sharing, and please enjoy the video. So first, let's discuss what the idea here actually is. I'll draw a plot. This will be A, this will be B, and then I'll do the same here. A, B. So the idea with fixed point iteration is that if I have some function, I'll just do a straight line because it's easier. And let's say that this is the point that we care about. Maybe I should zoom in. So this is the point that we care about. The idea here is that if I pick some random point in my interval, let's just say it's P0, then my function will map to a different point in this same space, within the same bounds. And so maybe we start here, and then we go, and it remaps in the same spot, and then we go here. This is P1. And then it goes again, and I land here, right? And so this is going to be P2. And then we just get super, super close by mapping the same point in the same space over and over and over again until we get sufficiently close to our actual point. And this point here is called a fixed point because, and it's defined that way, let me draw it here, because the evaluation, we'll just call this function g. So this line here, we'll just call it g, and it's called a fixed point at p if when you plug in p, it also equals p. That's it. And so this is sometimes an interesting problem to tackle because fixed points come up all over science and physics and econometrics, and a lot of applied mathematics has fixed points because that's sort of where equilibrium points lie. So this concept is a big deal and is also recurring. So keep that in mind as we go through this. But this is the idea for the algorithm. We want to be able to pick a point in an interval, and we want that to actually just approach the fixed point that we care about. So in this video, we'll go over proving that a fixed point exists. Like, so what conditions are required for this fixed point to exist? How many fixed points are there? What is the convergence of this algorithm? And what's the error bounds? So we're going to go over all of the numerical analysis here. Before we do that, we have two intermediate theorems that we have to know. So this is from real analysis. If it's been a while since you've taken real analysis, or you don't, or you haven't actually taken real analysis, I'll go through these very, very briefly. The mean value theorem. So you can think of this as the slope at a point is equivalent to the slope of a secant line at the endpoints. So if you have a continuous function, f, and f is differentiable on some interval, then there exists a number c, which goes here, in a to b, such that what I said here is true. So maybe I can draw you a sketch. Right, so here we go. A, B. And then you have, I'll give it like some squiggles. There you go. We'll call this guy f of x. And so what we're saying is that the secant line here, I'll just draw a line. So this is equivalent to, I'll just put C here. I don't know where it could be. This guy here is a tangent line. And so the slope of this tangent line is equivalent to the slope of this secant line. That's basically what this is saying in the mean value theorem, like geometrically. This is very useful. It comes up a lot. The next one is the intermediate value theorem. So given some f on some interval that's continuous, K is any number between the endpoints, and there exists some number C such that f evaluated at C equals K. This is very fancy stuff that's kind of worded, but this is really what's happening. Again, I'll draw you a plot. Okay, so I should do a negative to positive number. So A, B, start here, end here. And so the intermediate value theorem is really just saying that if I have two endpoints, A to B, this function is continuous. That means that 0 must exist as an example. So there must be some value C, f of C, that equals 0. And it must be continuous, because if it's not, then you can actually jump over this line, right? So really what it's saying is that given some continuous function, there exists points in between these intervals. So you can kind of just draw this line. And because this is negative here and positive here, 0 must exist. Like a 0 for the function must exist, rather. So these two theorems are important, and they will come up. So that's why I'm mentioning this now. First, fixed point theorem. So if g is a continuous function, and the function maps to the same interval that x is in, for every x in this interval, then g has at least one fixed point in that interval. So let's go through the proof. This is an existence proof for at least one fixed point. And also recall our definition of fixed point, right? So maybe I write it here. G of p equals p. All right, cool. So if the fixed point is on the endpoints, so if g of a equals a or g of b equals b, then we're done, right? We found at least one fixed point. If it's not on the endpoints, then that means that a is the lower bound, right, and b is the upper bound. So anytime then that we use this function g, it must be within this interval. And so that means that g of a is greater than a, g of b is less than b. So far, so good. We can define h of x to be this. Why did we do this? This is important. Well, see, but first, we can do this just by subtracting p over. So then g of p minus p equals 0. And then we just define that to be h of x. So nothing too crazy happening here. And then we define this on the same interval. And then we allow h of x to be continuous. And this is obvious because of our assumption that g here is continuous. Since g of a is greater than a, because we're mapping into our interval, it follows that g of a minus a is greater than 0. Right? So if this value is greater than a, and we're subtracting off a, it has to be greater than 0. Also, since g of b is less than b, it implies that this value here is less than 0. So, using the intermediate value theorem, this is what we just talked about. Using the intermediate value theorem, it implies that there exists a p-value such that this function has a 0. Therefore, we can conclude that g of p is equal to p. And so there must be a fixed point for g. And that's it. So this is why I mentioned that the intermediate value theorem is very important, because it allows us to demonstrate that there is a value in this set, and that this fixed point does exist. If the derivative exists on a to b, and a positive constant k is less than 1, exists with this bound. So this means that the derivative is less than or equal to 1, or at this point strictly less than 1, because k is. But if k is like 0.8, then it can be also equal to. And this is true for all x in the same interval. Then there exists exactly one fixed point in the interval. To show that there's only one, we're going to assume that there's two, and then reach a contradiction. So assume that p and q are both fixed points in a to b. So if p is not equal to q, then there must, then the mean value theorem implies that a number this is eta, exists between P and Q. And hence an A to B with this expression. So this is the mean value theorem that we talked about. And then we can sort of find then we can find an inequality that doesn't make any sense. So let's take the distance between P and Q. So remember that we're assuming that both of these things are fixed points. So that means that P is equal to G of P and Q is equal to G of Q. If you take the absolute value of this guy here and then do some algebra, you can get this expression. So this is equal to this, which is less than or equal to K times the same thing. But then we know that K is strictly less than 1. This is based on this assumption up here. So it doesn't make any sense for the distance between P and Q to be less than, or strictly less than, the distance between P and Q. So that's a contradiction. So therefore, the fixed point is unique under these circumstances. And that's the proof. Okay, so now we're getting into the meat and potatoes of our conversation. So this is the actual fixed point theorem. So let G be a continuous function and let it be in the same interval. So this is really the same conditions that we were working with before. So you notice that the first condition here shows that at least one fixed point exists, and then this next one, G prime, the magnitude of G prime, is less than or equal to K for all x in that same interval. That guarantees that there's only one fixed point. So this first is just a rewriting of the two proofs that we just did. Then for any number P0 in that interval, the sequence is defined by this guy. So this goes back to the idea that we talked about at the very beginning of the video, where we have decided that the function that we care about is going to map back into the same space and then inch closer to the point that we care about. It will converge to the fixed point. And that's what this is setting up. So for then any number P0 in this interval, the sequence defined by P sub n equals G of P of n minus 1 for all n greater than or equal to 1. And that this converges to a unique fixed point. All right, let's get into it. So since G maps into AB, into itself, the sequence, this guy here, is defined for all n greater than or equal to 0, and P sub n is in that interval for all n. Using the fact that this, right, so that the derivative is bounded by a number less than 1, and the mean value theorem, we have for each n, so this is the same argument that we discussed prior, so P sub n minus P is equal to G, so I am just using this substitution for this guy here into here. So this becomes G of P n minus 1, and then G of P equals P because that's the actual fixed point. This comes from the mean value theorem, and then this is also from the mean value theorem. So just some algebra. This is less than or equal to K, which is bounding this, and then carry this guy down. So where eta sub n is in the interval. So we're going to make an inductive argument. So let's go over a couple of them, just so we kind of get the intuition. When n is 1, using carrying this guy here down, when n is 1, P sub 1 is bounded by 1k and then P0 minus P. When n is 2, P2 minus P is bounded by k squared and then the same P0 minus P. So your initial guess minus the actual point. N equals 3, same deal, but k gets moved to the third power. So therefore, you can sort of inductively see how as n, if we want n iterations of this, it's going to be bounded by k to the n, initial guess minus the actual point. So since k is between 0 and 1, this limit of k to the n is going to go to 0. Therefore, as we continue applying this function in the same interval, it will go to 0. And then hence this sequence does converge. Last one, we have to put error bounds on our algorithm. So we know that it exists. We know that there's a sequence that converges to a fixed point. How do we go about quantifying how close this value will be given some n number of iterations? And so this is what we're going to do. So we have two different ones. This first one is the maximum of the initial guess to the endpoints. This kind of gives a rough estimate. Then this other one will tell you how close you get over many iterations. So the second one is more precise, but we will go over both. First, let's go over the first one. It's a more direct argument. So because p is in the interval, the first bound follows as this. So we take the nth iterator minus the limit point, and then that's less than or equal to k to the n p0 minus p. And so this is less than or equal to the maximum of this and this. So let's say that we make some random guess, and so it really doesn't matter where p0 is, so long as it's in the interval. And then let's just say that p is here. So the distance between here and here sort of gives us a really good estimator for how big this error is going to be. It's not a very precise one, but it gives you a good idea. And so this means that a sort of large error bound could just be the distance between b, this endpoint, and our initial guess, which is kind of true, because if we're just trying to get a decent idea of like how bad our guess is, or if this interval could be a solid guess, this sort of does the trick. It will help us understand, like, okay, is this actually going to do what we want? If we decide that in making some algorithm or doing an example that this is a bad guess, we can just shift our interval, or we can do other things to make a better first guess. So that's how I view the utility of this first bound. But the second bound is much more precise, and the second bound is better for actually computing the error of applying this algorithm. So for the next bound, we are going to borrow the same sort of logic from the actual fixed point theorem. So we know that given two points in our sequence, if we want the distance between them, this is again applying the functions, and then this is bounded by n iterators from applying this function. And so the nth plus 1 in the sequence minus the nth is bounded by the first two guesses by this scaling factor, multiplied by the scaling factor. And this is important to do this because it saves us a lot of time in figuring out how to compute this. Designing it so that we only need the first two elements in the sequence allows us to save memory, and it gives us a really nice way of figuring out how close this actually is. And so to really utilize this sort of formulation, we have to think of this not as like the point approaching a limit point, but as the distance between 2 points in the sequence. And so I think as I go through the argument, it'll make more sense. So take m and n arbitrarily, and so this can be like any 2 points in the sequence, and then we're going to just add 0. So p of m minus pm minus 1 plus pm minus 1. So this is adding 0. And then we're going to use the triangle inequality. And the triangle inequality is going to give us a sum of the distances between the current point minus the previous, current point minus the previous, current point minus the previous. Then we know that this is bounded inductively, so we can actually take out k to the m minus 1 iterators, right? And then the bound for that is going to be k to the m minus 1 multiplied by the first point minus the previous point. And do that for each and every single one of them. And then you'll notice that I can take out k to the n factors. And I do that here. So I take out k to the n, I get a 1. I take out k to the n, I'll get a k somewhere in here in this sum. And then all the way over here to the end, km minus 1. If I take out n, I'll get k to the m minus n minus 1. So this is just a factorization. So we know that a unique limit point exists. We proved that in the previous couple of hypotheses, and that's what we're using to prove this. Thus, as I take m to infinity, it will equal our limit point. So let's do that. So if I want my limit point, the distance between my limit point and where I am currently, I have to take the limit as m goes to infinity, and I have to take this guy there, right? And then this is bounded by k to the n. This is what we want in our expression in our theorem. And then this is just rewritten as a sum. So I took this guy and just rewrote it as a sum. Put the rest of it in there. Okay. And then this is less than or equal to, and then I'll just apply the actual limit. So, and the reason why this is less than or equal to is because here the sum is more finite, but as I add more terms, this will get, this will be larger, right? There's fewer terms here, there's much more terms here. And so that's why this is less than or equal to this guy, because this sum is infinite. But we know that k is less than 1 and greater than 0, so this series is geometric. So recall way back to Calc 2 that this infinite sum is equal to 1 over 1 minus k. And so all I'm doing here is taking this, plugging this in, and then I get our desired value. And so what this tells us about the convergence of our algorithm is that if k is closer to 0, this converges very, very quickly. So you want a smaller k. If it's very close to 1, it will take a while to converge, and it may not do it in a way that's beneficial for you. So sort of keep that in mind as you're using this. Smaller k value, better outcome.